Hey mathematicians, here are notes for 5.2 talking about direct variation. So for the bell work, write your own slope problem, then trade with a friend and solve. I suggest that you at the very least write your own slope problem. I'm not going to go through the bell work, I'm not going to write my own. There's plenty of other awesome math stuff to get into in this video. So if you want to go ahead and take a second to do that, go ahead. Otherwise, the goal for the day is I can define and calculate direct variation. Don't freak out by this big fancy phrase direct variation. It's just another type of slope. I'm going to keep pounding that into your heads. We have a lot of different names for slope, but at the end of the day, they all basically mean the same thing with just a few tweaks. So let's jump right in and look at a real life example. The total high-tech spending, represented by the variable T, of an average public college can be found using the equation T equals 203S, where the variable S is the number of students. Create a table to represent the relations and then graph. Now I do have a picture going on over here that's supposed to help us. It's kind of hard to read. I tried to make it as clear as I could, but I mean, it's an older picture. I could not do a lot with it. Maybe that helps a little bit. But basically, the picture is there for assistance. However, before we start, we need to decide whether T or S is the independent variable. So which one depends on the other? Does the number of students depend on how much the school spends? Or does how much the school spends depend on the number of students? In this case, the amount of money, T, that a school spends, the tech spending, is going to depend on the number of students that attend. You don't spend more money if you have less students. That doesn't make sense. So I'm going to set up my table here as students on the left and tech on the right. And then I'm just going to bring this equation down so it's a little closer, a little easier to find, so I don't have to keep going back to that word problem. So tech is equal to 203 times S. So let's just start putting some numbers in here and playing around with this idea. If a university has 0 students, meaning S is equal to 0, and I plug that in, I'm going to get 203 times 0 equals 0. So if there are 0 students, there's 0 tech spending. Hey, that makes a lot of sense. If I have 1 student, I can plug that in and say 203 times 1, meaning they're going to spend 203 on 1 student. Let's keep going with this. If they have 2 students, they're going to have 406 spent. 3 students means 609. And we'll stop at 4 just because the numbers are starting to get a little weird. But now that we've created that table, let's go ahead and graph it. I'm going to go ahead and say, I'm going to use 2 tick marks. So 1 student, 2 student, 3 student, 4, 5, we could go on and on. And then I'm just going to make the spending ticks about 203 per every 2. So 203, jump up again, 406, 609, 812. So 0, 0, no students, no spending. 1 student, $203 of spending. Maybe not $203. It might be more than that. Not real sure. 2 students, 406. The only reason I say I'm not sure is because $203 per student seems like a very arbitrary number. I would think that that would maybe be a little low based on today's numbers. Things are getting expensive, people, Things change. All right, so there is our graph. Notice I can also go ahead and draw a line up through here if I want, saying that if there's any students in between, yes, you can't have partial students, I know. But if these were larger numbers, if I had 10, 15 students, whatever it was, and there were students in between, it would indicate that there's a nice continuous relationship between how many students you have and how much you're spending. And as I said in yesterday's video, remember that direct variation is just another name for a positive slope. So notice, as my number of students I should have labeled these. As my number of students increases, so does my spending. So as X, let's get you set back up here. As X increases, so does Y. So this is an example of direct variation. They vary directly. All right, let's look at another one. A standard shower head uses about 6 gallons of water per minute. An eco-friendly shower head uses approximately 2 gallons of water per minute. Create a table below and then graph. All right, so let's start off, no minutes in the shower. Okay, now 1 minute in the shower, 2, 3. And now I'm going to switch my colors here. Hopefully we can see these. Because a standard shower head, it says that it uses about 6 gallons of water per minute. So let me think here for just a minute. Do I want to write an equation? The amount of water used, so water is equal to 6 gallons per minute. So each minute we're in there, we're going to multiply it by 6 to get how many gallons of water were used. It's just a simple equation. You don't have to write it, but it helps me think a little bit. So at 0 minutes, 6 times 0 is going to be 0 water used. Totally cool. At 1 minute, that's 6 gallons of water. At 2 minutes, that's 12 gallons of water. At 3 minutes, it's 18 gallons of water. Our eco-friendly shower head, on the other hand, I'm going to use the orange here. The water is equal to 2 gallons per minute. So each time we plug something in here, we're going to multiply it by 2 gallons. At 0, we're still at 0. We're good to go there. 1 minute uses 2 gallons. 2 minutes uses 4. 3 minutes uses 6 gallons. So there is our table. Now let's go ahead and graph that. The minutes are obviously going to be on the bottom here. The water used is going to be on the left. So this is minutes. This is gallons. And I'm going to graph both. That's also why I chose a different color, was because I want to be able to see both of them on the graph. So at 0 minutes, we've used 0 gallons. At 1 minute, we've used 6 gallons. At 2 minutes, we've used 12. And at 3 minutes, we've used 18. Now, even though those are all separate, at a minute 30, the water is still running, so there is an amount of water being used in between there, meaning I'm going to connect these dots so that they're nice and continuous, and then it goes up, up, and away. Let's go ahead and do that eco-friendly one next. There we go, get you back focused in. At 0 minutes, no water used. At 1 minute, we only have 2 gallons. That's about here. At 2 minutes, we've used 4 gallons. It's about there. At 3 minutes, we've used 6 gallons. With that, when I connect the dots, it's going to look something like this. All right. So let's compare and contrast the graphs of each shower head. Are they both direct variation? Well, as X increases for the standard shower head, the gallons increases. That makes sense. The longer you're in a shower, the more water you're going to use. It makes sense then that the eco-friendly is also a direct variation graph. So compare, they're both direct variation. Notice, even though they're both direct variation, one does not have such a tall slope. This one is definitely growing, but at a much slower rate of change than this one is. In fact, you can see with our standard shower head, it took us 1 minute to use 6 gallons, whereas with our eco-friendly, it took us 3 minutes to use those 6 gallons. So you can see how slow those are changing, and their rate of change is obvious in the equation too, because one is changing with the slope of 6, much taller, whereas the second one is changing at a rate of 2 gallons per minute, which is slower. There's plenty more we could talk about, compare contrast with that. But the main thing I wanted you to see was that even though they're both direct variation, they can change at different rates, and that's okay. So last thing here, by now we should recognize that direct variation is a specific type of slope, just like rate of change is. What makes direct variation special, or what is its special characteristic? Now I think this one's a little bit easier to see if I bring down these equations. So my first equation was t equals 203s, w equals 6m, w equals 2m. Notice none of them have numbers behind them. So none of these equations say like plus 10 or plus 15 or anything like that. They all technically start with plus 0. Now that might not come naturally to you. That's okay. Being a math teacher for a longer period of time, I've started to see that. It's okay if you don't. The thing that makes this special, the reason why this is important, is because the number that is behind whatever is going on in front tells us where our graph is going to start. And direct variation specifically starts at 0 in both of these cases. Now it doesn't have to, but notice that as one increases, so does the other. They all start at 0 and they all increase. So on this page specifically, those are the special characteristics for direct variation. Pretty soon we're going to be getting into some indirect variation where we're working with a negative slope. But in this case, we also notice that all of our slopes are positive. All slopes are positive. What were the other ones I listed? All slopes are positive, they all start at 0, they're all increasing. However you want to say that is totally fine as long as you see that these direct variations increase and go upwards. Alright, I know that there can be a lot of questions with direct variation, so if you have any confusion or any questions on anything I went over, please don't hesitate to let me know. I'd love to help you out.